Hey everyone. So in this lesson, we're going to be building on some of the things that we have talked about so far in Unit 4 about quadratics. So just to recap, you have done work with complex numbers, right? And you learned a lot about what a complex number is and what it means, as well as how to perform operations with complex numbers and simplify imaginary numbers, right? So you've learned about I and how you simplify I and really what I means. You've also done work with factoring and solving by factoring, as well as solving by completing the square. In this lesson, we're going to use our knowledge of quadratics that we've talked about and just the background knowledge you have, as well as a large focus on completing the square to solve for intercepts and solutions. And we're going to actually prove and apply the quadratic formula. So the quadratic formula is, I would hope, somewhat familiar to you. It is something you've used in the past. Maybe you had like a little song or a little tune that helped you remember it. One of the things I'm going to guess that you probably didn't do is prove it, right? And really understand like where it's coming from and how it's kind of just a manipulation of other things that we've done to solve quadratics. And that's why this is the third one that we're doing. And just what the different pieces mean and indicate to us. We're also going to look at applying them. I want you to also keep in mind that you, in the past, when you maybe did quadratics in general, and this has been true for this entire unit, focused a lot more, or focused only really on real numbers. And while real numbers are great because we can see them on our typical XY coordinate plane, right? We're going to be solving this over the set of complex numbers. And that's why in this objective, we have written that we would solve for intercepts, which would be the real solutions, as well as just all the solutions in general. No matter what, when we're dealing with a quadratic, there are going to be two solutions. Okay, that doesn't mean that there's going to be two x-intercepts. That doesn't mean there's going to be two places that this crosses the x-axis. There could be none. There could be one. There could be two. But we're going to be solving this over the set of complex and not just the real number system. So our answer is never going to be no real solution, right? We want to know what is that non-real solution. So with that being said, let's get started. Let's start with a review of solving by completing the square. All right, so if you, I currently have this, and there's a variety of different ways to go about this. I have this set equal to 0 right now. My goal is to solve, so I'm going to go ahead and actually subtract that 5 from both sides. So I'm just rearranging. You're allowed to, it is legal math to add something to both sides, right? But it's got to be the same something. So I need to figure out what is going to make this a perfect square. So I'm going to figure out what exactly can I add, and I got to do it to both sides, that's going to make this factor into a perfect square, make this the area of a square, right? And so maybe you remember what exactly we do here, but we take b and divide it by 2 and then square it, so that we're getting that number that when we add it to itself gives us b, and when we multiply it to itself gives us c. So that's going to give us, what is this going to be, a 1? So we're going to end up with x minus 1 squared. That's equivalent. That means I have to add 1 to this side as well. So that's going to give me -4. And then we can go ahead and square root both sides. So that will give us x minus 1 equals plus and minus. This is the same thing as 2i. Remember, we were the first ones that wrote that. It is always going to be the positive and negative. The square root of -4 is 2i. And then I can go ahead and add 1. So you've got x equals 1 plus or minus 2i. And those are my two solutions, right? 1 plus 2i, 1 minus 2i. So that means that if I were to take this and graph it and said it was equal to y and actually graphed the quadratic, the entire thing is going to happen above the x-axis. I don't actually know where it is. I'm not focused on that piece of it. That was actually pretty good. 1, 4 would be the vertex. We'll talk about that a little later. But the whole thing would happen above it. Let's do another one. Ooh, so for this one, I have this coefficient right here, but I noticed that all 3 terms are divisible by 3. And so I'm going to go ahead and actually start off by dividing everything by 3. Even the 0 is getting divided by 3. Right? So you've got x squared minus 4x plus 5 equals 0. And then I'll go ahead and do the same process. X squared minus 4x equals negative 5. Let's figure out what's going to make this a perfect square. Make that the area of a square, and I got to do it to both sides. So I would have x minus 2 squared here. So this would have to be a 4. So this would have to be a 4. Equals to negative 1. When I go ahead and take the square root of both sides, I get x minus 2 equals plus or minus I, the square root of negative 1. Don't forget that plus or minus. So I've got x equals to 2 plus or minus I. Again, entire thing is going to happen above the x-axis. If I didn't divide by 3 and instead I factored it out, that would be absolutely fine. Okay, so this one's already moved over there. So now I just got a x minus 14x plus something equals negative 10 plus something. Remember, it's always adding there. Because if you square a number, it's positive. It's going to be a real number. So this would have to be x minus 7 squared. So this would be 49, and this would be 49. Equals, what is that, 39. So when I go ahead and I take the square root, you've got x minus 7 equals, what is that, 3 times 13. So it's not simple, it can't be simplified. Plus or minus the square root of 39. So x equals 7 plus or minus the square root of 39. So I get 2 real solutions here. And irrational. That's what that means. I'm not going to go into a calculator. We haven't picked that up yet. So this means that if I were to graph y equals x squared minus 14x plus 10, it would cross the x-axis twice. Right? Or, oh, it's equivalent. I can come down here. Y equals x minus 7 squared minus 39. Right? Oh, I could have done that too. Cool. They're the same. They may equal the same thing. We'll talk about those forms soon. And then finally, this one right here, which, oh darn, they're not all divisible by 2. So here's what I'm going to go ahead and do. So I'm going to start it off the same way. 2x squared minus 5x equals 8. And I know I need to add something to both sides, right, to complete the square. But before I can do that, before I can complete the square, this just needs to be x squared, not 2x squared. I need to factor out that 2. So I've got 2. X squared minus 5 halves x plus something equals 8 plus that same something. But I need to remember I factored it out of every single number here. Every single one. So that 2 will stay there for a few minutes. And I will go ahead and and I guess I could have just divided everything by 2 also. I just figured I would do it this way. This would have to be x minus, if I divide this in half, 5/4. So this is 25 over 16. If I double that, I get 50 over 16, which is 25 over 8. We're going to add 25/8. So this would be 64/8. 64 and 25 is what? 89? 89/8. And then I'll divide by 2. Maybe I should have done that at the beginning of this or earlier on, and that's fine if you did that as well, but it's okay to see different methods of the same setup. So I'm going to divide by 2, or that's the same thing as multiplying by 1/2. I have to do that part of it first. I cannot take the square root first. You're going backwards through order of operations. You're undoing something. So when I do that, I get 89 over 16, which I don't know if that can be simplified. Yeah, I don't think it can. So I'm going to leave it as 89 over 16. And then I will go ahead, and now it's the same process, right? So we're not going to be afraid of fractions. You are able to deal with them. So that gives me x minus 5/4 equals plus or minus the square root of 89 over 4. right? You're taking this. I don't need the plus or minus in both parts. It's just plus or minus root 89 over 4. It's either in the numerator, in the denominator, or out front. It's not in both. That's unnecessary. 89 cannot be simplified. I don't think, at least. Right? I definitely don't think it can. Square root of 89, no. That's not rational. Okay. And then I'm going to go ahead and add 5/4. Oh, I lost my pen. Oh, there it is. So you got x equals 5/4 plus or minus the square root of 89 over 4, which if I really wanted, I can leave it like that. So I get two real irrational solutions. If I really wanted to, sorry, I'm going to go up here. I could write this as 5 plus or minus the square root of 89 over 4. Oh, maybe that looks a little familiar to you. Maybe. Where we're going? Right? So really, when we're solving quadratics, our first line of defense should be, can we factor? Is it something I can solve by factoring? Because that's going to be our quickest method to do this. Is it a trinomial? Is it a perfect square? Is it difference of squares? Can I solve it by group? Can I factor by grouping? Can I factor something out? Right? Regardless. If you can't, try completing the square to solve for x. Right? If that doesn't work either, that's really where we want to turn to the quadratic formula, which you might remember. I haven't even said it yet. So given standard form of a quadratic, we're going to actually complete, right? This is standard form. Complete the square, you leaving a, b, and c. So do the same process we just talked about on those 4 problems to actually solve for x. Okay? So I would love right now if you pause the video and tried it. See if you can do completing the square with ax squared plus bx plus c in order to solve for x. So hopefully you gave it a try, and let's go ahead and do this together. So the first thing I'm going to do is I'm going to divide everything by a. Everything. Even the 0. So this is going to then leave me with x squared plus b over ax plus c over a equals 0. I will then go ahead and subtract c over a, right? Just like you do. And if you subtracted c first and then divided, that's fine as well. Okay? So now you've got to remember, we're going to be adding something to both sides. Well, how did we figure out what that something was? We took that middle term and divided it in half and then squared it. So take the middle term and divide it in half. So b over a divided by 2, or times 1/2, is where b over 2a is coming from. And when you go ahead and you square it, you get b squared over 4a squared. Every single part gets squared. Okay? When you go ahead and so like I'm adding b squared over 4a squared, b squared over 4a squared to both sides. When you go ahead, this is now a perfect square, and this is what we get, right? X plus b over 2a squared equals negative c over a plus b squared over 4a squared. Right? So I'm not actually changing any. I'm not doing anything. I'm just rearranging. I'm just completing the square. That's all I'm doing. I'm trying to isolate x. Okay. So our next step would be what? Let's get a common denominator and actually combine these, right? Can't find my pen again. There it is. So in order to get this common denominator of 4a squared, I had to multiply this one by 4a over 4a, right? And that's where negative 4ac plus b squared, negative 4ac plus b squared over 4a squared. Now I'm going to go ahead and square root both sides. Okay, so what happened here, right? So when I took the square root of both sides, no more square root here, took the square root of both sides, it's plus or minus, don't forget that. And all that happened here is we just switched the order, and maybe you're starting to see why we're switching the order. So b squared minus 4ac all over 4a squared. Well, when you take the square root, you can take the square root of the numerator and the denominator. You're able to break it apart like that. Like the square root of 2/4 is the same thing as the square root of 2 over 2. Okay, that's how square roots work. So if I have the square root of 4a squared, well, the square root of 4 is 2. The square root of a squared is a. So that's just going to be 2a. So this is the same thing as the square root. So this right here is b squared, the square root of b squared minus 4ac all over 2a. And then we can go ahead and subtract b over 2a. Right? And oh, maybe this looks familiar. Does it? This right here is the quadratic, what we know as the quadratic formula. Right? So no, for those of you that are like, oh my gosh, am I going to be asked to prove the quadratic formula? No, you won't necessarily be asked to prove it, but it is extremely important information for you to see that these things don't happen in isolation, right? The things that we're learning, when you begin to apply it and you go farther into this, they're connections that are going to benefit you if you can make those connections and see that I'm not learning these 3 separate methods. I'm learning these 3 things that are intertwined that can be used to prove the other. Okay, so this is really, and the quadratic formula is really like our last line of defense. So quadratic formula can't be used in the place of factor. It can help us to figure out if something is factorable. It can help us to figure out if there's real solutions or imaginary solutions, or if there are actually x-intercepts. They do support each other, but we're not like, this is solving, and this is really our last line of defense. But the reasoning behind it is critical, right? So here you've got negative b plus or minus the square root of b squared minus 4ac all over 2a is what x is. No, this is not a formula that's going to be like written on a formula sheet. You do need to know the quadratic formula. So let's use the quadratic formula to find some solutions, right? So right here, I actually changed this up. I'm giving you the equation of a quadratic. As we've talked about, when we're saying find solutions, solutions are intercepts. I want to find x-intercepts. Well, when we're dealing with x-intercepts on a graph, and this is a quadratic, you're talking about where your y value equals to 0. So my first thing I'm going to do is go ahead and plug in 0 for y. I'm really saying, when I'm saying find solutions, it's find x-intercepts. That's true with every single equation and function that you deal with. Okay, so it says to use the quadratic formula. So I have x is going to be equal to the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. Show your setup. Find it. Negative 7 plus or minus the square root of, what is this? 125 plus 120? 145? All over 10. Okay? I'm going to go ahead and I want to simplify 145. Right? So 145, let's see, can I simplify that? What happens? No, I can't, because isn't it 5 times 30 would be 150, so it's going to be 5 times 29, which both of those are prime. So this cannot be simplified. That is my solution. Right? So I ended up with 2 real irrational solutions. I'm not putting this into my calculator. I haven't even picked up a calculator. Either should you. Let's try another one. So same idea, right? So I'm going to go ahead and my first thing is I should be plugging in 0 for y. X equals 2. And even if you can do something else, even if you're like, oh, I know how to factor this, or I'm going to do completing the square, like I'm asking you to do the quadratic formula. That's what you're being asked to do. Negative b plus or minus the square root of b squared minus 4ac all over 2a. So x equals 2, negative 10 plus or minus the square root of 12, 24, 36, 48. So 100 minus 48, 52, all over 2. So negative 10 plus or minus the square root of 52 all over 2. Let's see, is 52, can that be simplified? If I divide that in half, I get what, 26? Right, so that's going to be x equals -10 plus or minus 2 root 13 all over 2, which means I've got -5 plus or minus the square root of 13. I want to emphasize that we should not be getting, like, again, I've got two real irrational solutions here. I want to strongly encourage you to simplify radicals, right? However, it's not, if you are not successful at it, it's okay, right? It takes practice, and I want to encourage you to practice simplifying radicals because it is something that's going to benefit you, right? Like, imagine if you were doing something where it's like, hey, one of these is the solution, and it was simplified. You want to recognize that there's equivalent forms for things. There's different ways that things can be represented. So if you're just asked to solve, it's okay if you don't simplify, right? But it doesn't mean that you shouldn't be trying, and you shouldn't be practicing and working towards mastery of that. Okay, so if you haven't paused the video to try any of these on your own, please do so at this point. Okay, I've only gotten real solutions. So x equals minus b plus or minus the square root of b squared. I would really please make sure you're showing your work. All over 2. So you've got x equals to -5 plus or minus the square root of -3, 25 minus 28, all over 2. In the past, you may have stopped here and said, no real solution. We know how to simplify this, though. The square root of -3 is the same thing as I root 3. Right, so -5 plus or minus I root 3 over 2. And that is where we need to stop at. This is not far enough. You can simplify that more, and you should simplify that more. Right, so this means that I have two non-real solutions. Right? Oh, I wrote over it, sorry. I'll go over here for the second one. So x equals -6 plus or minus the square root of b squared, so 36 minus 4 times 9 times 1, all over 2 times 9. -6 plus or minus the square root of 36 minus, what is this, 9 times, 36, all over 18. This is just 0. So you've got x equals -6 over 18, which is just going to be -1/3. So here I had one real solution, and one real rational solution. That must mean that the x coordinate of my vertex is -1/3. Isn't that pretty cool? This means that if I were to graph this, and hey, I could plug in that -1/3, 9 times -1/3 squared plus 6 times -1/3 plus 1. And that gives me 9 times -1/9, positive 1/9 plus, what is that, -2 plus 1? This is just 1 minus 2 plus 1, 0, right? Which makes sense. That's why I only got one solution there. So that means that the vertex, and you guys can check me on this one, if you went into your calculator to graph this, which eventually we're not going to need to, you would get -1/3, 0 is the vertex. So that means that so it's just -b over 2a. And the third one here, oh no, where's c? That must be 0. So x equals -3 plus or minus b squared minus 4 times a times c, all over 2. -3 plus or minus the square root of 9 over 2. -3 plus or minus 3 all over 2. So then it breaks off into 2. -3 plus 3 is going to be 0. So that's one of my solutions. It's rational and real. And then -6 divided by 2. So x equals -3. Amazing. Okay, so b squared minus 4ac. Let's talk a little bit more about that. That is called the discriminant. The discriminant can tell us, so if a, b, and c are rational numbers, then when the discriminant is positive, when the discriminant is negative, and when the discriminant is 0, we can tell different things, right? So this is the part that's under the radical. Notice the radical is not part of this. b squared minus 4ac. It's not the square root of b squared minus 4ac. It's the part that I would be taking the square root of. So b squared minus 4ac, if it's positive, it means that my solution is going to be real. If the discriminant is negative, it means that it's going to be non-real, right? You would end up with the square root of a negative. If the discriminant is 0, that means, so here you're going to have 2 real, here you're going to have 2 non-real, here you're going to have 1 real, right? And your x-intercept is actually going to be the vertex, right? So you can tell a lot of things through this reasoning. You can also tell what it means if it's a perfect square. So meaning if it's positive 25, or if it's positive 9, or if it's positive 16, it's going to be rational. Oh, sorry. If it's not a perfect square, it's going to be irrational. So when I've been writing, and I've been writing this out, right? So if your discriminant is positive, you could use this reasoning to be like, okay, I'm going to have 2 real rational solutions. If you aren't able to factor, but you check if you're having trouble factoring, and you check the discriminant and you get a positive perfect square as your discriminant, keep trying to factor. You can factor. If you get a positive number that is not a perfect square, so like 13 or 21, right? That means that it was an irrational. Just your solutions are going to be irrational, and it makes sense that you weren't able to factor it. Okay, if you get a negative, that means that you couldn't have factored it. Okay, if you get 0, you could have. Keep trying. Okay, so you can use this reasoning to really help you. So use the discriminant to tell what kind of solutions the equation below has, hence find the solutions, right? So you're first going to figure out what kind of solutions. So I'm going to go ahead and b squared minus 4ac is the discriminant. Notice I don't have the square root there. So 10 squared minus 4 times 3 times negative 1. Sorry, I had a moment there. So that's going to give me 100 plus 12. 112 is your discriminant. Okay, so I now have that. So that means that I have 2 real irrational solutions. Hence, so that means that I'm going to continue working with what I've already done. I'm not going to go back and try to complete the square, right? So now I'm going to go ahead and I've got negative, sorry, I'm having a moment. Negative b plus or minus the square root of 112 all over 6, right? So is 112, can that be simplified? Yes, right? Yeah. So let's see, 112, what's the largest perfect square that goes into 112? 16, right? 16 and 7. So the square root of 112 equals the square root of 16 times 7, which is going to be 4 root 7. So you've got negative 10 plus or minus 4 root 7 all over 6, which means that you've got negative 5 plus or minus 2 root 7 all over 3 would be my solutions. Okay, so this is called discriminant reasoning. You're expected to know this word, and you're expected to know what is indicated by discriminant reasoning, right? So I am using discriminant reasoning to solve this, to figure out how many solutions that I have. Okay, this right here is discriminant reasoning. This was not something I could have factored. If I was told to factor this, I wouldn't be able to. Factoring is not a possibility. I couldn't solve this by factoring. Okay, hence means that you continue with the work that you've already begun. It doesn't mean you go back and redo it. Okay. So we're going to use this same reasoning, discriminant reasoning, to tell whether or not the function ever has the given y values, right? So will this, whoa, weird, ever equal to 6? Well, when we're finding solutions, you're basically, when you're finding solutions, you're saying, will y ever equal 0? Right, so will y ever equal 6? Well, let's find out. 6 equals 3x squared plus 10x minus 1. Well, in order to use the quadratic formula, I need to have this equal to 0. So 3x squared plus 10x minus 7, right? So like what's happening here is right now, let's say I've got a parabola that opens up. And here's x equals 6. I'm basically, when I just subtracted that 6, I'm just shifting everything down 6, right? So like it's like you're just translating it. That's all that's happening when we're subtracting that 6 from both sides. So I could have just done that right away if I had wanted as well. To make that like my new intercept, kind of. Okay, so discriminant reasoning, b squared minus 4ac. So I've got 10 squared minus 4 times 3 times 7, 100. Oh, is that a negative 7? Negative 7. Plus, what is that? 12 times 7 gives me 84. Right? Yeah. So 184 is my discriminant. So using discriminant reasoning, yes, it will intersect y equals 6 twice. I know that because I have a positive number, right? It's not going to be at 184 is not a perfect square, so it's not going to be at rational numbers, but it will intercept it twice. What about negative 10? Right, so 0 equals 3x squared plus 10x plus 9. So I would end up b squared minus 4ac. My discriminant would be 100 minus 4 times 3 times 9. So that's 100 minus 4 times 3 times 9 gives me 108, which gives me negative 8. So will they ever intersect? Nope, they won't. That's my discriminant. My discriminant is negative. So that's going to give me 2 imaginary solutions, which means that it doesn't actually have an x-intercept on the real coordinate plane. So this graph will never actually intercept y equals negative 10. Okay. So in this lesson, we reviewed some of the things that you have learned about quadratics and a little bit with imaginary numbers as well. And so keep practicing. And kind of tied in completing the square to figure out where the quadratic formula is exactly coming from. We also talked about discriminant reasoning and using the discriminant. So again, like we've now learned how to solve with factoring, with completing the square, and with quadratic formula. And so at this point, you got to practice, right? And recognize that if you're not told which one to use, you can use any of them, but how can you do need to be able to successfully use all 3 when asked, okay? And use each one to help yourself out, right? If you're not sure how to factor, like, well, was something factorable or was it just prime? Was the answer prime? And you can use something like the discriminant reasoning to help you with that. So please make sure that you continue to practice and use the resources there to practice, as well as complete your part 1 of your homework assignment. And we will see you all next time. Whoa.